So now, key in homologous structures. Homologous structures arise from a similarity from common ancestry. This is known as homology. So when I have a structure that is going to be similar to another organism, and we both share a common ancestor, so we are both related in some way. I want to stress out that common ancestor. We do have a relation. That is known as homology. So basically, these are characteristics that have changed over time. They've been modified. Darwin coined this descent with modification. This occurs by natural selection, what he described in his theory of evolution, as descendants face different conditions. So different environments will form that structure in different ways. These are homologous structures. What I want to point out before I go further in those bullet points, so here's a human, and here I've highlighted the human limb, portion of it anyway. I can actually see the distal arm here, the portion of the arm further away from the midline of the body. This is actually going to be the radius of a human, and a couple of different bones by the hand are highlighted here, as well as the fingers. These are known as carpal bones, and these are actually known as phalanges, so just the bones in our arms are highlighted in brown. Okay, so I have orange, yellow, brown in a human. In a cat, I can actually see a limb as well, and I can see how those bone structures are modified a bit differently from the human. Well, if I look at the whale, I can additionally see that those structures still exist, but they are modified as well, and then a bat also showing those modifications. These are called homologous structures. A human, a cat, a whale, and a bat will have a common ancestor. And I will tell you if they have a common ancestor or not. I don't expect you guys to know that a bat has a common ancestor with humans. We do. This will be clarified in your questions. Common ancestry with these different characteristics that have been altered over time is are homologous structures. So characteristics are similar yet function differently. So the similarity here between all these characteristics that I'm showing you is that they are the forearm or a limb of a creature. That's true. What a human might use that limb for over here, well, I'll look at the cat since, you know, my Google Slides toolbar doesn't hide that. So over here, the cat, what that cat will use that limb for walking, for pouncing, for jumping, is going to be a little bit different from what that bat uses that limb for flight, for grabbing. That whale is going to use that limb as well for different things as well, for swimming, for propelling. And so the functions can be different. Darwin cited that these anatomical similarities among the vertebrae, so these are all vertebrae that I'm showing you guys, they are evidence of common ancestry. So again, I just want to point out homologous structures. These are characteristics that are similar, resulting from common ancestry. They might function differently, yet they are similar. Vestigial structures are the next structures that I want to go over. And vestigial structures, you're not really comparing between two different organisms. They're more so remnants of features that once had an important function in the ancestor. Now, in modern organisms, they don't really have a function. They are evolutionary leftovers. So you might be able to think of a couple of vestigial structures on your own. Some examples I want to show here in the whale. There's a pelvis. You're going to see this in your lab, actually, that's brought up in your simulation. A vestigial structure is the vestigial pelvis here in the whale. So it's kind of free-floating. It's not really attached to the vertebral column, as you can see here. It's actually a remnant of what the ancestor had, the pelvis and some hind limbs, or a leg, if you will, attached to the structure. Well, the whale doesn't really need that anymore. A whale is not on land and is not mobile on land. It's not terrestrial. And so the vestigial pelvis has stuck around in this organism, but is no longer useful. So that's called a vestigial structure. The ancestor does have hind limbs attached to that pelvis for the whale, which you will find in your simulation. The muscle in humans called the Erector Pele attaches to hair follicles in the human. And have you ever gotten goosebumps before? So your hair kind of sticks up and you kind of see goosebumps being raised on your skin. Maybe you're cold, you get goosebumps, or maybe goosebumps just happen to you for some reason. That's a vestigial structure in humans. It's a really neat vestigial structure because what that muscle does is it's kind of working in our fight or flight response when we used to have more, when our ancestors had a lot more hair than we did. And whenever we needed that fight or flight response and we needed to warn off other animals, our Erector Pele muscles would then cause that hair to erect and cause us to look more intimidating. We really don't look intimidating now because we don't have as much hair as our ancestors did, but we still have that vestigial structure, that muscle that's going to erect our hair whenever we need that fight or flight response, or maybe we're cold. And so that's just a really neat vestigial structure that we can see here. We see a cat. I'm showing you that fight or flight response. That cat gets scared and then all that hair just gets erect. And that's the Erector Pele muscle working for that animal. That cat's trying to look larger than it really is and trying to be intimidating. Honestly, this cat doesn't look very intimidating, but that's probably how we look when our hair is being erected by this muscle because of our ancestor actually having more hair than we do. Another example that I want to use in the human is actually the coccyx. So this tailbone here, we actually do have a vestigial tailbone. It's known as the coccyx. So these are coccygeal vertebrae that exist in our vertebral column. And as we age, adults actually fuse these bones together, but they're less fused when we're young. And these are remnants of a tailbone. I did have a student one semester that knew somebody that had pronounced tailbone, and it actually grew a little bit more than normal, I should say. And so it kind of protruded from the tail end of the vertebral column. And that is very much a thing. You can have a different number of coccygeal bones, and some just have more than others. Normally, they don't protrude. This is a vestigial remnant coming from a common ancestor that had a longer tail. Analogous structures are the next structures that I want to go over. And I want you guys to think of analogous structures when you study homologous structures. So I want you to compare the two. They are different. So analogous structures have a different structure. So they're not homologous. They have a completely different structure with a similar function. Remember that homologous structures didn't have to have a similar function, like the bats could fly with their forelimb or the cat can walk with their forelimbs. That's a very different function, but they were similar in their ancestry. Well, now in analogous structures, they have a similar function, different structure. Basically, guys, I'm telling you, there is no common ancestor in analogous structures. So this is going to be the wing of a bat and the wing of a bee. Wing of that insect is going to be very similar in function to the bat in that they're both going to use that wing for flight, but there is no common ancestor. This is not homology, and I will tell you when there's common ancestor or not. Another example is the forelimb of a penguin and the dorsal fin of a dolphin. These are analogous structures in that they are going to use them for a very similar function, swimming, propelling through aquatic environments. It's going to help them with that, but there is no common ancestor with the dolphin and the penguin.